Alright, so today we're going to do this problem. Alright, so we've got a ball rolling down a hill. And shit. We've got a ball rolling down a hill, and it's going this way. This is the velocity of the center of mass. This is gravity. This is going to be friction. And then it's rotating like that. There we go. Yeah. This, of course, is a right triangle. Alright, and then we can, it's going to be, this is going to be mgx, which is going to be mg times sine theta. Alright, and then here we've got theta. And so first I'm just gonna derive a formula real quick, because we're trying to find the linear acceleration, right? So I'm not gonna use these numbers right now, because I don't need to. So I'll just use symbols for them. Alright, so basically you've got your force of gravity acting down, and you've got your mg sine theta acting down the slope, and your force of friction acting up the slope. So we know Newton's second law says F net equals ma, and really we're trying to solve for this. So basically you got to find the F net first. And the F net's gonna, well, we know it's moving this direction, right? You know it's moving down the slope. So we're gonna take the force that's going down the slope minus the force that's going up the slope. So that's gonna be mg sine theta minus the force of friction. And that's gonna equal m times a, right? Okay. Now, we also know that there's a torque on the ball because it's rotating. So we're going to say, all right, we know that the equation for torque is torque equals rotational inertia times alpha, which is the angular acceleration. And we also have our equation for angular acceleration, which is linear acceleration equals r times alpha, which is angular acceleration. Then we can rearrange that to find angular acceleration. So alpha equals alpha equals a over r, and then we can just plug that in. So that's going to be equal to I times a over r. And since torque is going to be, the net torque is going to be also equal to RF times sine theta, so R times net force, radius times net force, right? So RF sine theta. Well, actually in this case it really doesn't matter, since over here we've got our force of friction. It's it's acting, you can see that's going to be an angle perpendicular. I guess you can't really see that. Or no, you can't really see that either. Wait a sec. There you go. This is going to be an angle perpendicular. Uh, so it's going to be 90 degrees. So we know sine 90 equals 1. So this doesn't really matter. But yeah, so it's going to be r times F net. Or rather, no, it's going to be r times the force that's causing the torque. So basically it's going to be r times FF because force of friction is causing the torque, and mgx is really not because it's coming straight out of the thing. So it's not causing a torque. It's not what's causing it to rotate. If there weren't any friction, it'd just be sliding. Yeah, so then you can plug that stuff in, and let's see. All right, so then we can use that to get an expression for force of friction. So force of friction, we're going to rearrange the torque equation equals I times A over r squared, because we took the r and we divided it on that side. Okay, and then we got mg sine theta, because this force of friction is going to go into there, right? Minus I times A over r squared equals ma. All right, and then we're trying to find A, right? So like we can yeah, so we can put all the terms with A on one side. So we got ma plus ia over r squared equals mg sine theta. And then you got A times m plus I over r squared is going to be equal to mg sine theta. And then you can just divide all that shit on the other side. So A equals mg sine theta over m plus I over r squared. And I think that's pretty much it. And if you want, you can divide the m's on the top and the bottom. So we got g sine theta equals 1 plus I over mr squared. All right, so that's for the acceleration. But now we can also rearrange that if you want to find like, um, inertia, which is the I in the equation, right? So you can multiply everything in this here equation because it's easier to use. Or actually, no, scratch that. You can just multiply everything in this equation by r squared, right? To get rid of that denominator. So r squared ma plus I a equals mg sine theta times r squared. All right, and then we can take out the a's here. So a times r squared m plus I equals mg sine theta times r squared. And then you got r squared m plus I equals mg sine theta r squared over a. And then we can just subtract the r squared m to the other side. So yeah, so I equals, or whatever, mr squared, I guess, mg sine theta r squared over a minus mr squared, right? And yeah, and we can actually just factor out an mr squared. So I equals mr squared times -1 if you want to do that, plus g sine theta over a. Yeah, and that's going to be your equation for, let's put that in a box. Ooh, special red box. Okay, so that's going to be your equation for inertia there. Let me make that a little bit smaller. There we go. All right, yeah, so that's going to be your equation for inertia. And then we can just plug shit in and get our answer, basically, because, yeah. All right, end of video.